Good. So thank you, the organizers, for organizing this PiNE event. So I will talk about the semi-martingale methods, and I will have 3 lectures on this. So I'll talk about the Foster-Lyapunov methods for Markov chain, and then Conrado will focus on talking about interacting particle system and martingales. And George and Frankie, next week we'll talk about linear random growth and scaling limits. So what I'm going to cover, so I've just covered the course outline. So first of all, I will introduce you some background material on martingale, and then I will give the recurrence and transient criteria, and then I will talk about the positive recurrence criterion, and then I will give 2 long examples on random walks on half strips and a photo model. Okay, so these 2 will be in the second and the third lecture. So for this lecture, I will focus on the first 3 things. Right, so first of all, I want to talk a bit about the material that are used in this lecture. So most of the knowledge and most of the theorems are actually from this book. So this is a good book, very good book, non-homogeneous random walks. And it mainly focuses on this method, the semi-martingale method, or sometimes in the literature it's also called the Lyapunov function method. Okay, so, and here is the 3 authors. You just saw Andrew, and I think Mikhail is also in the audience. And this is the second book that I use for these lecture notes. So it's topics in the constructive theory of countable Markov chain. Is also a very useful and classical book that a lot of theory that I cover here is in this book. Okay, so these are the 2 main reference books that I'm following. And so I'm grateful to Andrew for the discussion on these topics of this lecture. And I'm also thankful for Nick for the template of these slides. So I will give more reference at the end. And when I use a particular reference at some point for a particular theorem, I will also state that. Right, so let's go for the martingale background. So let's start with a Z. Okay, so Z equals to Zn, n is in Z plus, is a real value discrete time stochastic process adapt to the filtration Fn. So let's recall what a martingale is. So a process Zn is a martingale with respect to the given filtration is if for all n greater than or equal to 0, we have the following 2 conditions. So the first condition is expectation of the absolute of Zn is finite. And also we have the expectation of Zn plus 1 minus Zn is equal to 0. Okay, so for this 0 case, because Zn is a martingale, if this equal sign is replaced by greater than or equal to, then this is called a martingale. And reverse, if it's less than or equal to, then we call this a super martingale. So let's recap 2 theorems, 2 standard theorems on the martingales. So the first one that we'll use quite a few times in this course is the convergence of non-negative super martingales. So suppose Z greater than or equal to 0 is a super martingale. Then there is an integrable random variable Z such that Zn will converge to Z almost surely as n goes to infinity. And we also have expectation of Z have an upper bound of expectation of Z0. Okay. And we also have the next theorem, which looks quite similar, but is on 2 stopping time here. So suppose again Zn is just a super martingale greater than or equal to 0. And suppose we have 2 stopping time, sigma and tau. So tau is the bigger sigma at the bigger stopping time. Then we have the expectation of Z tau is less than or equal to expectation of Z sigma. So you see when we take the expectation, the order is reversed because it's a super martingale. Both of them are finite. And we also have the expectation of Z tau given all the information that we have, given the filtration of F sigma, this expectation is less than or equal to Z sigma. Okay, so again, this is the bigger stopping time. This is the bigger one, and we condition on all the information before the first one. Okay, so these two facts we will keep on using in this course. They are very useful facts that we'll see later. And so before we talk about recurrence and transience, I want to give you the following theorem, which is in some sense separate, but a very useful result. So let's set n be an integrable Fn adapted process on R plus. So we are thinking on R plus now. So suppose that for some b, also in R plus, we have this condition. So in some sense, you can think of this as the jump, and this is the expectation of the jump. So we have this less than or equal to a constant b almost surely. So essentially it means that we have bounded jumps in the setting. Then for any step n and any x greater than 0, we have this condition. So this condition says when we look at the maximum of this process z in between 0 to n in this period, and the probability of this maximum is greater than or equal to z is less than this value. Okay. Right. So let's try to prove this theorem. So in fact, it's quite straightforward. There's only a few steps. So okay, let's tau be a stopping time. Okay, any stopping time. Then first of all, we observe that we can have this relation here. The expectation of this set minus this one is less than this thing. Okay, so this one, if you don't know about the notation, this is the minimum of n plus 1 and tau. Okay, so we have an indicator function here. So let's look at the two cases. If tau is greater than m here, then when you take the minimum, the tau disappear because the tau is a bigger one. So we have set m plus 1 minus set m. Okay, this is exactly b, right? From the condition that we have previously. And if it is not, then we just have set tau minus set tau, which is 0. Okay, so we also have the correct bound here. Okay, so after we have this line, we take expectation on both sides. So we take the expectation, the condition here, Fm is gone, okay, and the indicator function becomes probability. Then we sum up, do a telescopic sum from m equals to 0 to m equals to n minus 1. Then you see when we add up the left-hand side, then all the middle terms cancel. So all we left with is the biggest term, which is expectation of Zn wedge tau minus expectation of Z0, which is the smallest one. Okay, then we have the sum here. So if you look at this sum, we can actually bound it by the expectation of tau, right? So just a simple observation here. So when we take this tau to be n wedge sigma x, okay, then we essentially just replace this tau with n wedge sigma x here. Okay, then we have the following condition. So we rearrange the, okay, so there's no rearrangement here. So Bn is just greater than B of times expectation of tau, which is greater than or equal to this quantity here. Okay, but in our setup, we said that set n is always greater than or equal to 0. So this quantity, set n wedge sigma x, is just greater than or equal to x times the indicator function, which is essentially this when we write it out. Okay, this is exactly the same thing of saying this. Okay, so if we go back, everything, this is the line that I promised you to prove. Okay, it's just do a rearrangement of putting the set x on the other side, then we get this. Okay. Right, so here is an example of why the theorem is useful. The theorem that we just say is useful. So, is it something? Okay, so let's have a simple symmetric random walk. So define Sn to be a simple symmetric random walk, and theta here is just the increments of each step. So we sum up all the increments, give us the random walk. Okay, and this random walk is on Z. Okay, so it's just a one-dimensional random walk. So we let Zn here to be Sn squared. So we're looking at the square of the random walk. Then when we do this, so what we aim to get is this line. So we after we do, if we apply the thing above with Zn equals to Sn squared, then at the end we get the probability of maximum of Zn, Sn. That is what we are interested in. Okay, so let's see how we do it. So we follow what we have before. We want to calculate Zn plus 1 minus Zn. Okay, so this is just Sn plus 1 square minus Sn. Okay, expand this. This is just the last step. And then we get this, okay, by cancel out the first term. So you take the expectation here. So we can break the expectation. We get this and this. So for simple symmetric random walk, the expectation of each step, the drift of each step is just 0. And the expectation of this one is 1, right? Because it can only jump left 1 step and jump right 1 step. So this expectation is 1. So we plug in everything, apply the theorem, then we have the probability of this maximum of Sn greater than or equal to x is less than or equal to n divided by x squared. Okay, so essentially we see how far the walk can go to. If you want it goes beyond x, then the probability is just n divided by x squared. Okay, so in this case, Zn is a submartingale. So one can just use the Dupes inequality to get the same result here. Okay, so there's another way to show this result. Okay, so let's continue. So if we let un equals to this quantity here, so this complicated quantity here, okay, then we can actually replace the x here that we have just before with this un. Okay, then we have this condition here just by replacing all the numbers here. So it seems that this is a rather weak bound, but if we consider a subsequence here, then we can actually get a very good bound here. So we want to consider the subsequence n equals to 2 to the power k. K is greater than or equal to 0. So if you apply Baruch-Cantelli, it shows that the maximum of all the things within 0 to 2 to the power k of this Sm is less than or equal to u to the power k. Okay, because we are taking a subsequence here. Just replace n with 2 to the power k. Okay, so for all but finally many k, and any n, in n we always have this condition, so we can always find a smaller kn, a power of 2 to just and another power of 2 by one more power bounded in between any n. So for all but finally many n, we have this condition. Okay, so we can have the maximum of Sm is less than or equal to maximum of Sm, but we replace this n with Skn plus 1 because we can take a bigger maximum of a bigger region. Okay, and this one is just bounded by u2 times 2 to the power kn minus 1. So you just put the number here into here. And this, if you look at how we define u just now, then this is just 2un. Okay. So in here, what did we show? We have shown that for any epsilon greater than 0, for all but finally many n, then we have this thing here. Okay, the maximum of Sm is less than this. Okay, so in some sense, this is a very good bound because it tells us how big we should expect this Sm to be. for, say, if we run S for n step, then the maximum in this period will have this bound. So we see how big S can be. Right. So this is the end of the Martingale background. We'll move to the recurrence and transient criteria. So this is the main theme of this series of talks. So let's talk about the recurrence classification first. So what is recurrence and transience? So I think this is somehow the most intuitive way to interpret this. So suppose that Xn is an irreducible Markov chain on a countable state space sigma. So you see, I am not using Z anymore here. I will use X to represent an irreducible Markov chain. So if I use Z, it means it is just a general adaptive process. But if it's X, then I mean it's an irreducible Markov chain. Okay, so on a countable state space sigma. So we call this Xn to be recurrent. This will mean that with probability 1 for every X in this sigma, Xn is equal to X infinitely often. So what this means is for any fixed point X, this process Xn will keep on coming back to this point. Okay, and in fact, this is a class property. So if it visits one point infinitely often, then it will visit all the points infinitely often because the Markov chain is irreducible. Okay, so on the other hand, if it's a transient, then it means that with probability 1 for every X in sigma, Xn is equal to X only finitely often. So in some sense, it means that after the process Xn visits a point X, then it will finitely many times, and then it will go away and never come back. Okay, so that's what it means by transient. So we also have the notation positive recurrence here. So what it means that there exists a probability distribution pi on sigma such that if we look at this, if we take the limit of 1 over n summation of this indicator function of this xk is equal to x, then we get a stationary distribution here, pi x. Okay, so what this means is if we fix x and then we try to look at, well, when this x this back x can be equal to x in this period 0 to n. Okay, sum up all the number of times that visit this value. Okay, and then we just take the proportion here. So the number of times visit this value x from 0 to n divided by a total number of steps here n. Okay, it's essentially the proportion of time that the process will spend at this point, and then we take limit n goes to infinity. Okay, and that's the stationary distribution. Okay, so if we assume some aperiodicity here, then we can actually just get probability of xn equals to x converged to the stationary distribution pi. Okay, so this is somehow the most intuitive meaning, but in terms of use this kind of meaning, there's actually quite a few equivalent definitions in the literature. Okay, given the fact that we have irreducibility here, and we will use the strong Markov property heavily here, and then we have this set of definition, which is a lot more useful in our setting. So for fixed A in sigma, we define that tau A equals to this minimum. So this is stopping time, or sometimes we call this hitting time. So it's the first time that this process go into this region A. Okay, that is what this stopping time is. So we call X is recurrent if for some finite set A, probability of this stopping time is less than infinity, given that we start xn start at x is 1. Okay, so this probability is 1. So what it means that in a finite time, then it will always go back to this region. Okay, so this is very similar to the thing that we just stated before. we just somehow write it in a different way. Okay, so on the other hand, if it is transients, then it means that for some non-empty A, we have the probability of this tau A equals to infinity is greater than 0. Okay, so it means that it has some chance that it takes some chance that this stopping time is actually infinite, so it will never come back. So if it's positive recurrence, then it's about expectation of this stopping time. So for some finite A, we want this expectation of tau A is finite. So it means that in expectation, we should wait for finite amount of time, then the process will come back. Okay, so this is positive recurrence. So in here, this case, if it's recurrence, it's not necessarily that the expectation is finite here. Okay, it can be infinite. If it's finite, then it's positive recurrence. If it's infinite, then it's now recurrent. Okay, so there's the famous theorem on simple symmetric random walk called the Ployer's recurrence theorem. So what it says is that the simple symmetric random walk on ZD is recurrent in 1 or 2 dimensions, but it is transient in 3 or more dimensions. Okay, so there's a quote by a Japanese mathematician, Shisho Kakutani. So it kind of captured the theorem in an easier sense. So it's somewhat equivalent to the theorem. It says that a drunken man will find his way home, but a drunken bird may get lost forever. Okay, because a drunken man will walk on a 2-dimensional plane, which is recurrent. So eventually it will go back to its starting point. And the drunken bird may get lost forever because the bird flies in a 3-dimensional space. So it is possible that it will never come back. Okay, so here's some simulations. So these 3 lines, this blue, red, green are 3 separate trajectory paths on 2-dimensional simple symmetric random walk. So you see it kind of travel through here from dark to a lighter color for all 3 colors. So the theory tells us that it will always come back again and again for any points on the plane infinitely many times. Okay, so if it's a 3-dimensional case here, then the thing will be transient. Okay, so again, this is 3 simulations this is the typo on a 3-dimensional and simple symmetric walk here. Okay, right. So in some sense, our point of interest here is if we are given general irreducible Markov chain Xn, okay, we want to decide this process when it will be recurrent and when it will be transient. Okay, so the main idea is to achieve this kind of criterion. So if we can check certain criterion is satisfied, then we have the Markov chain being recurrent, or on the other side it will be transient. Okay, so here is one of the main theorem in this course. So this is also called the recurrence criterion. An irreducible Markov chain Xn on a countably infinite state space sigma, okay, is recurrent if and only if there exists a function f and a finite non-empty set A in sigma, such that we have this condition hold. So if we take the expectation of fxn plus 1 minus fxn, okay, given we know the starting point start with x, if this expectation is less than or equal to 0 for all x in sigma outside of A, so any for all points that is outside of non-empty set A. And the second condition that we need is we want this fx goes to infinity as x goes to infinity. Okay, so if these 2 conditions, if we can find an f such that these 2 conditions are satisfied, then we can show that xn is recurrent. Okay, so in some sense, most of the time we will use the if part here, although the question is stated in the only if part. So what we try to do is we will try to find a function f that satisfies this condition to show that the process that we are interested in is recurrent. Okay, so this is the side that most of the time we will use. So this theorem, a weaker version of this if part of this theorem, is actually dealt by Foster in 1953. Then it is improved by Higgs in 1969, and then the only if part is proved by Mertens in 1978. Okay. Right, so before we go for the proof, let's try to have a simple example to see why this theorem is useful. So let Sn be a simple symmetric random walk on Z2, okay, and we consider Fx to be this thing. So this time I tell you immediately, so what is the correct function, or we call it the Lyapunov function, to pick in order to make this work, make this proof work, is to take Fx to be this thing. Okay, so we have a parameter here, so gamma is something in between 0 and 1. Okay, so essentially we need to do a calculation here that I'm sure that every one of you can do. So just do a Taylor expansion here, and so we can calculate the expectation here. Okay, so we can calculate this expectation. So after a bit of calculation, you get this big thing. Okay, so if you look at this, well, this is positive, this is positive, this is positive. So if gamma is in between 0 and 1, then this one will be negative and this one will be positive. So overall, the whole thing will be negative. Okay, and more importantly, we also see that this thing goes to infinity as x goes to infinity. Okay, so it satisfies both conditions in the theorem. So we prove that Sn is recurrent. Okay, so essentially we prove part of the Ployer's theorem here, because what it says for a two-dimensional random walk, a simple symmetric random walk, this random walk is recurrent. Okay, so it's part of the Ployer's theorem, which is different from the original proofs by Ployer. And this theorem is actually, if we provided that if we have this theorem in our hand already, then to prove the Ployer's theorem is just a few steps here. So it's a very powerful theorem to use here, because there's only a few steps here, then we can already prove that Sn is recurrent here. And later we'll try to do the other side. In fact, if for the transience side, a very similar calculation can be done here. Okay, using a different theorem. Okay, so let's try to prove this theorem. Again, the if part is the important part, is the useful side most of the time. So we will just go through the if part proof. Okay, so we take x0 equals to x in sigma. So we fix x0 here. And then we set yn to be this thing. So f of xn wedge tau a, the meaning of n and tau a. Okay, then we can actually see that yn is a non-negative supermartingale. Okay, so well, by the theorems in the martingale background, then we see that yn is converging to y infinity almost surely for some y infinity, and we have the expectation of y infinity given the starting point is less than expectation of y0. Okay, expectation of y infinity less than expectation of y0, and y0 is just fx here. Okay, by definition. So on the other hand, so since this f goes to infinity, it holds that the set, this y in sigma fy less than m, okay, is finite for any m. Okay, so if you look at this set, okay, the set of all the y's that is less than a certain fixed number m, okay, then this set is finite. So by irreducibility, this implies that the lim sup of this fxn is positively infinite, almost surely, on this event. So when this stopping time tau a is infinite, then we will have the lim sup of this fxn is positive infinity. Okay, so because of this, so if we consider y infinity, we should have the same result, because y infinity is just the limit of yn, because this lim sup is equals to positive infinity, so this limit is also positive infinity, so we have this. Okay, but then this is actually a contradiction. So why is that? It's because this contradicts to the inequality here. Okay, so if we assume that there's some probability that this event that we condition on is actually happening, so probability of this is actually greater than 0, then when we take the expectation of this thing, we'll have infinity. Okay, but this can't be happening because this is less than or equal to fx. Okay, which is so there is a contradiction here. So that's why this event is actually never happening. So the probability of this stopping time equals to infinity is 0. Okay, and this means that the process is recurrent. Okay, that's just from the definition of what recurrence means. So the probability of this less than infinity is 1, right? Okay, so you see the proof is actually quite straightforward. It's not particularly long, but the theorem itself is very useful when we applied it. Okay, so in fact, we have a very similar result on the other side, which we call the transience criterion. So let's have a look at this. An irreducible Markov chain Xn on a countably infinite state space sigma is transient if and only if there exists a function f and a non-empty set A such that this condition hold. Okay, so this condition is exactly the same as the one that we have for the recurrence side, but this condition is different. So what we need here is we need Fy is less than the infimum of everything x in A of Fx, okay, the infimum of Fx, for at least one y outside of this set. Okay, so you see, because of this condition is different, so most of the time, if we want to prove something is transient, we need to take another function. So this function most of the time is different than the one that we use in the recurrence criterion. So in some sense, a process is either recurrent or transient. So one side will essentially fail. Okay. So on one side, if you're doing the wrong side, then it means that you can never find a function to satisfy both conditions here. Okay. And if you pick the right function and pick the right side, then you can get this result. So in some sense, you can see these theorems are very robust here. So okay, so a weaker version of this theorem is again due to Forster. So what Forster have to do is, instead of considering a non-empty set A, a general A, he consider just a point here. But essentially, it gives the same theorem here. Okay, then is again improved by Mertens et al. In 1978 to give this form here. Okay, so as promised, let's go for the example first. So we'll prove the other side of the Ployer's theorem. So let Sn be a simple symmetric random walk on set D this time. So what we are trying to achieve here is we want to prove that when D is greater than or equal to 3, the walk is transient. So let's see how we do this. So this time we take a completely different function, the Lyapunov function here. So let alpha is greater than 0 and consider this function f from set D to 0, 1. And defined by f0 is just 1 and fx is this quantity. Okay, it's the norm of x to the power minus 2 alpha. Okay, so again, we do a Taylor expansion here. The Taylor theorem will give us the calculation here. So we want to calculate the expectation of fsn plus 1 minus fsn. So after the calculation, you have this quantity here. So again, we want to show that this is less than 0. Okay, so for x is sufficiently large and alpha is greater than 0 here, so this is positive, this is positive. So we want this thing to be negative. Okay, So to make this negative, we want to take alpha in between this region, 0, d minus 2 over 2. Okay, if we can have this region, then when x is sufficiently large, then this one will be negative. Then we have this condition here. Okay, but be careful because we need alpha to be in this region. So this region need to be exist first. So we can only take d is greater than or equal to 3 here. Okay, because if we take 2, then it's 0, 0, then the region it doesn't exist, or 1, then it's 0 and a negative number here, so it doesn't exist again. So it got to be greater than or equal to 3. So this is exactly why the walk this proof only works for d is greater than or equal to 3. Okay, and when d is greater than or equal to 3, then this proof works. So we show that the simple symmetric random walk is transient. Okay, so
Hugo, we have a question from Frankie here.
yes.
He's asking, how should we be thinking of A, capital A? And is it z squared, a picture of a ball around the origin? This is a typical picture.
Yes, I mean, in general, A can be any non-empty set. So as long as it's work, then it's okay. So I mean, the two sides is kind of slightly different. So for the recurrent case, you want to find a finite non-empty set A to satisfy this condition. So in here, what you can do is usually it will be a set that is around the origin, which can be crazy, can do whatever it wants because it doesn't matter as long as the tail behavior is good enough. So that is why this condition we only needed to satisfy for all x outside of this region. Okay. So usually it is this side, this A is the side that does not matter in terms of recurrence and transience. Okay. Because only the tail behavior in this kind of things matter. Okay, so we are only thinking of what will happen when the process essentially you wait for a long time, and after it, and you can ignore any finite region in this kind of situation. Okay. So, right. Yes. So we want to prove this theorem 6. We want to prove this transient criterion. So before we can prove this theorem, we need to establish a lemma first. So although the theorem looks very similar, but the proof is completely different here. Okay, so let Xn to be a Markov chain on state space sigma. So suppose F is measurable and A is such that this same condition hold, again, the expectation here. Okay, and then we also have the this condition on this Xn outside of this region. Then we have this probability here. So the probability of this stopping time is actually finite. Okay, given f0 is less than or equal to this quantity. Okay, fx0 divided by infimum of fx. So we want to prove this. So we set yn equals to fxn wedge tau a. So it's the same setting that we had before. Then we can see that yn is a non-negative super martingale. So again, yn is goes to y infinity almost surely. And by optional stopping, we have this condition here. So because it is a super martingale, so the expectation of y infinity is less than or equal to y0. Okay. And we can artificially add an indicator function here, which just makes this smaller. Okay. And now we consider the thing in the expectation. Okay, so this thing, y infinity times this indicator function, is that there's a typo here. So it's the limit n goes to infinity and yn of this. So essentially, by definition, y infinity is we take the limit n goes to infinity here. Okay, so this is just fx tau a by definition here. Okay, and this is just greater than or equal to the infimum of fx. Okay, so we have this quantity here. So if we look at this, then we see that fx0 is just y0 by the setting here, which is greater than or equal to the probability of tau a less than infinity times this. Okay, so what we have done here is just take the expectation. Okay, then we have to. Okay, so we're done. Rearrange, we will achieve this fact. Okay, so in fact, if we have this lemma, then proving the theorem for the if part again is very straightforward. So we just have the same setting. So with y, this is outside of set A, then the lemma actually show that this thing is less than 1. Okay, because what we did here is we just replace the condition here, x0 equals to y, then we just have this. Okay, so this is just a proportion of this, so this will less than 1. Okay, and this is essentially what we want. Okay, if we go back to the condition, this is what we want to achieve here. Okay, and we already showed this. So we have proved the theorem. Okay, so this gives transience. Okay, so how much time do I still have? About 10 minutes. Okay.
About 20 minutes.
Oh,
little less.
20 minutes. Okay.
Yes, yeah, a little less.
Okay. So the next thing I want to talk about is the positive recurrence criterion. Okay. So in some sense, we can achieve a very similar theorem, but on positive recurrence here. And so this is the Forster criterion. Okay. But before that, let me present a theorem first. So let Zn, which is a positive real number, be integral, which is inside the positive real line, be integrable, and Fn adapted. Okay, so Zn is a process, and let this tau to be a stopping time. And if we assume that for some epsilon greater than 0, this expectation again, Zn plus 1 minus Zn is less than or equal to minus epsilon, then we can actually show that the expectation of tau is less than or equal to the expectation of Z0 divided by epsilon, which is finite. Okay, so this is a general theorem. This is on Z, so it's not just on Markov chain. So as long as it's an integrable and adapted process, then this fact holds. Okay, so again, is a very useful fact, because if we have this condition satisfied, then immediately see that the expectation of any stopping time is finite, and we have this condition here. So let's try to do the proof. So if you look at the condition that we have here, we can try to rewrite it in this form. So again, this is again a trick how to add the indicator function here. So one can check if the indicator function is equal to 1. If we have this condition, then this side is exactly the same as the condition that we just stated before, so it's less than epsilon. And if it's the other side, then we just get 0 both sides. Okay, so the reason why we want to do that is we want to get the probability here. So the method that we are doing here is very similar to what we have just done in theorem 3. So we take the expectation here, so the conditioning is gone, and separate the expectation, and the indicator function becomes a probability. Okay, and we do the telescopic sum, okay, and rearrange. Then we have this expectation is less than or equal to the expectation of Z0 minus epsilon times this sum of probabilities. Okay, so again, it's the same method. We take n goes to infinity here. Then expectation of tau is just the limit of the sum of this probability. Okay, and by this condition here, because this one is greater than 0, so this thing is less than or equal to the expectation of Z0 divided by epsilon. Okay, and these two are constant. These two are things that we know, so it's finite. Okay, so we have the positive recurrence criterion here, and this is also called the Foster criterion in the literature. So an irreducible Markov chain Xn on a countably infinite state space sigma is positive recurrence if and only if there exists a function f and a finite non-empty set A and epsilon greater than 0 such that these two conditions hold. So you can look at this condition. So this one is for anything that is outside A, and we want this expectation, this very same expectation is less than or equal to minus epsilon. Okay, so this condition is stronger than the one that we have seen before. So for the recurrence criterion and transient criterion, we only need this thing is less than or equal to 0. But in here, we need this thing to be less than or equal to minus epsilon. Okay, and we also need expectation of fxn plus 1 is given this starting point condition is finite. Okay, for anything that is inside the region A. So in here, you can see that for most of the time, we need a different function than the one that we use in recurrence. So most of the time, if we want to prove something is recurrent, we can pick a simple function to make it work so that those conditions works, but we can only guarantee that this expectation is less than or equal to 0. But then if we want to prove something is positive recurrence, usually we need to work harder so that we need to find a better function to satisfy this condition. Okay, so we will see this later. So again, a weaker version of this theorem is still to Foster, and then it's improved by Mertens et al. And Molden. So in fact, to prove this theorem is very straightforward once we have known the theorem before. So this is theorem X. I think this is a typo. It should be theorem X, the theorem before. So if we had this theorem, okay, we just apply this set is equal to fxn, okay, and with stopping time tau a. So instead of stopping time tau, we have stopping time tau a here, and then for this set n plus 1, we have fxn plus 1, and then everything follows. Okay, it's just as simple as that. Okay, so again, although the proof is very simple, but it's very useful. So let's have a very good example here. So this is a longer example, and this example is due to Hanifed and Pidenger in 1990s. So let's cite.
Sorry,
yes, is it? Should I stop here? Yes.
If it's quite a substantial example, it might be best to leave it to the next session.
Okay.
Because
okay.
we've only got 4 or 5 minutes.
Okay, then maybe I should stop here and leave the audience for questions, and then we will continue this example in the next hour.
Sure, Deblina, go ahead. You're welcome.
So this, I don't know if you're going to cover this probably in the next upcoming slides. So can everybody hear me?
Yes.
Yes.
So my question is something maybe, I don't know. So if you have this Markov chain, say on a countable state space,
yes.
And you have all the nice properties, that is, it is irreducible, positive, recurrent, and aperiodic. So you have a stationary distribution pi. But suppose in addition to this, you have something like a Doblin's criteria, like the rate of convergence is uniform over the whole state space. Then is there a version of Foster-Lyapunov theorem for that?
So you have some extra condition here. So what is the extra condition that you said?
So extra condition is that if you go back to the first few slides, say where you define the irreducible aperiodicity. So this is more in, so yeah. Yeah, here. So the third bullet, you have this probability of xn converging to pi of x, right? So here, if you have, in addition to this, some uniform rate of convergence for all states x, so that means probability of xn equals to x minus pi x, and you take the absolute value of that, and you take supremum over all x in your state space sigma, and you say that, okay, that is less or equals to some constant times some rho to the power n, where rho is a number between 0 and 1. So basically, this is converging. This is, the rate of convergence is uniform. Right? I think this is known as the Doblin's condition in the language of Markov chains. So for that, can we find something that gives like some equivalent of this Forster-Lyapunov condition?
Right. So I think in this case, we are not talking about positive recurrence here, right? We are talking about something else that we want.
Yeah, it's the rate of convergence. Like you would probably get that if you have a finite state space, always such a uniform rate of convergence. And I don't think you even need a periodicity in that case. But for an uncountable state space, if we can find some Lyapunov function f, then maybe we can, that's something. Just I was working on something and I felt that these two are related. So I thought that maybe I ask you if you know something.
I'm actually not sure. We do have some stronger version of this Forster criterion, which essentially give you more precise result on the moment existence. So how many moments of this stopping time exists?
Okay.
So this might give you more structure on what you want to do. I'm not sure if that will satisfy the condition that you just said.
Okay. Okay, thank you, Chak.
Yeah.
So is there any other question? Well, I have a question. May I ask, Hugo?
Yes, go ahead.
Why do you call it Lyapunov criteria? What is there a relation with what's the Lyapunov standing?
Oh, it's the Lyapunov function. So it is. Essentially, I think. Well, this kind of function actually exists somewhere else in physics, which they call these kind of things Lyapunov functions, and we try to borrow their name there, and call this function as the Lyapunov function. So in the literature, most of the time we will call this either semi-martingale method because it applies the sum fact with super martingale or some martingale, and the function we will most of the time call this Lyapunov function. It's just we want to find the function that satisfies that condition, and in some literature, that condition, if a function satisfies that condition, that is called Lyapunov function, because it is, well, probably first state by Lyapunov.
Excuse me, it's Mikhail. I can tell you the history. It's about because with Vadim Malchev, when we thought about these functions, we use this title or name because of differential equations. In differential equations, Lyapunov functions are to study stability of some differential process, and it's very similar to these differential equations criteria. So it was my opinion how it happened like half century ago. Okay, thank you.
Yes, thank you.